version, substituting one function inside the other. I think we had left off with, again, MyOpenMath loves presenting functions in all different types of ways. Pre-calculus is about functions. Here you present it with 2. And we're talking about composition. The street version says that we're really talking about arrows. We're really talking about arrows. First one says, look, what is this thing going to do to 5? G is going to transform 5 to some other number, then F is going to do something to that. All right, so we'll burn through these. G is going to take 5, change it to 1. We're then going to apply F to 1. The answer is 3. Apply G to 5. This is sort of funky because they write G in the 3rd column, but it's okay, right? Here, I'll take any questions on why that's 3. F is going to take 7, make it 6, and then G takes 6 and leaves it as 6. F is going to take 8, make it 9, and then F takes 9 and makes it 4. Transforming. And then when you apply G twice to 6, looks like G is a fixed point. Right? So G takes 6, keeps it as 6, but then apply G to that again, it stays 6. 6 is what we call a fixed point. It does not change under G. 6 is a fixed point for G. It doesn't change. So is there just another way of looking at it? Composition. Same thing, just in graph form. G takes 0, makes it 3. F then takes 3, makes it 4. F takes 4, makes it 2. G then takes 2 and changes it to 1. F takes 5, makes it 5. Oh, 5 looks like a fixed point. 5 just goes to 5 no matter how much you apply F to it. F of F of F of F of F of 5 is still 5. G of 2, G takes 2, makes it 1. Then G takes 1 and makes it 5. Right, just applying functions. We do this all the time, right? We take something, apply functions to it. Anything here super challenging? Here we're just in the midst of algebra, right? So we're going to take all of G, plug it into F. Yeah, and then I'm going to take any questions about this assignment. Look at anything that might be super challenging. F of G, street version, take G, plug it into F. 3 times 3x squared plus 2x plus 5 now becomes a question of how much we want to simplify. Right? F little circle G of x is equal to f of g of x, which is equal to 3 times g of x plus 5, right? And then g happens to be this function, right? Can't go wrong if you write 9x squared plus 6x plus 15. I'm tripping. Plus 5. The trade does not distribute. Questions there? I'll have a conversation with my TA about grading this test. But again, please make sure that you execute the test in a way that no grader, no matter how bad the grader is, has to mark everything correctly. Substituting. Oh yeah, this one just looks ugly. So the question is, so this is an exercise in algebra. The question becomes, how bad can we put this in? Anyone try to do the minimum for this, and my math lab still took it? My open math still took it? So we're practicing algebra here. The game plan remains the same. Wherever there's an x, put the other function. F of g of x is equal to 1 over g of x minus 3. Now this actually turns out to be okay, right? This is equal to, so instead of this x, you put the entire function g. So this is 1 over, g in this case is 7 over x plus 3. Should actually put that in another color. So it's like you're substituting in this brand new function here, 7 over x plus 3, and then minus 3, right? Which actually is not so bad. 1 over 7 over x, x over 7. You flip it. F of g of x. G of f of x. We're going to take all of f, put it in the g. That's not so bad either. G of f of x is equal to 7 over the function f of x plus 3. This equals 7 over, what are we plugging in now? We're plugging in 1 over x minus 3. We're about to flip that for sure. Plus 3, right? 7 times x minus 3 plus 3, and we'll simplify as needed. 7x minus 21 plus 3, right? 7x minus 18. There, hopefully. 0 to 10. 0 being too easy, 10 being impossible. How are these? So yeah, again, there's some algebra issues. Yeah, but I'll definitely give you one like this on Friday. Six. More practice. 7. F of g of h. Someone sent me an email about this one. Right, so street version, take h, plug it into g, take all of that, plug that into f. When you plug h in the g, it gives you a new function. Whatever that function is, take all of that, plug that into f. So we work inside out. G of h of x go to G, plug in H. G takes a number, subtracts 9. So it's going to take H and subtract 9, right? That thing, right? And then F of G of H of X. F takes a number, raises it to the fourth, and adds 6. So it's going to take G of H of X, raise it to the fourth, and add 6. So it's the square root of X minus 9 to the fourth plus 6, something that we would not simplify. So we're not intimidated by plugging multiple things into itself, right? So please go ahead.
You would have boiled it out.
I'm not interested in you raising that to the fourth power. Yeah, no, and again, this is good. So me as a grader here, and you know, Coach Young is not going to care either. This problem was never about raising something to the fourth power. This problem was about, do you know that you're substituting in, right? And if I see this as the grader, it's clear to me that you fully know what you're doing about this concept. This concept is about substitution, not about raising to the fourth power, right? And so again, that's the mark. That's my job. My job is to make sure that I get problems that you aren't just doing just because, right? We don't need to be wasting time raising stuff to the fourth power. We know how to do that. Eight. All right, so divide. Oh, so here are domains, right? So here's the funky issue. We're going to know the domains of these functions. We're going to divide one function over the other. They actually don't want to know the functions themselves as much as they just want to know the domain. I've got m over g of x. Here's m over g of x. M over g of x. So we now know we've got some problems, all sorts of problems here, right? We can simplify this. This is equal to 1 over the square root of x times x squared minus 4. We'll put this in red. So we got some problems with the domain. Divide by 0, root, and even root of a negative. These are things we do not want to do. All right, go ahead.
What property allowed you to just move the square root of x into
Oh, like that. Thank you. I appreciate that. So the question is here, right? So then let's move down. How do we get that, right? We do this a couple ways. Here we go. Okay. So I've got 1 over a over b, right? So the fraction's 1 over a all over b. And so this is equal to 1 over a divided by b, right? Is that okay? When you divide by a number, it's the same as multiplying by its reciprocal. So this is 1 over a times 1 over b, right? And this is equal to 1 over a times b. Is that okay? Yeah, so you can, thank you for that clarification. So you can't just throw the thing right down to the bottom. Other question?
Yeah.
Excellent, excellent. Hold me accountable. My goodness, I love it. All right. Divide by 0, even root of a negative. So that means that we're going to set the denominator equal to 0, and we're also going to make sure that we're only taking the square root of positive things. So this means that if this is issue 1 and this is issue 2, then to handle issue 1, we just need to make sure that the square root of x times x squared minus 4 is not 0. So we find all the places where it is 0 and get rid of those places. Again, by the zero property law, this means that the square root of x is 0, or it could be that x squared minus 4 is equal to 0, in which case x is 0, or x squared is 4, or x is equal to 2, or negative 2. Those are all places that ruin the denominator, and so those are all places that we would like to avoid. Please.
About the example was right there, the 1 over a over b.
Yeah.
Isn't 1 over a over b equal to 1 over a divided by 1 over b?
Is it? So say that again. Isn't 1 over a
over b equal to 1 over a divided by 1 over b?
Divided by 1 over b. That?
And then you flip it, multiply.
And so then this is equal to, you're saying that this is equal to 1 over a times b?
Yeah.
Which is b over a?
It's not what it is.
So this is good. So, okay. I appreciate you saying this. So we've got, this is what's bad about complex fractions. So I got 1 over a over b. And I've got 1 over a over b. Okay. One of these, oh, and let me write it over here. I've got 1 over ab, and I've got b over a. Okay, so I've got 4 things here. I need to match them up. Okay, so I want to be clear that the first one is I want to take the fraction 1 over a, and I'm going to divide that by b. The second one is I have 1 divided by the fraction a over b. So now it's clear that these things aren't well defined, because now you have to, it depends on how big you draw your fraction bar, right? So one of these is 1 over ab, and the other one is b over a, right? If I'm taking 1 over a over b, that's b over a, right? Because yeah, you do flip, right? But what we had was, we had 1 over the square root of x divided by one thing, right? Which makes it this. Is that okay? You see the difference?
Yeah.
Yeah. That's right. Thank you for that clarification. Okay, great. Yeah, so here it would have been like, it would have been different if this was 1 over the square root of x over x squared minus 4. Right? That's the difference. Yeah. It is not that. All right, so I want to avoid those places, and then I have this funky square root. We just need to make sure that I have the square root of x. I need to make sure that the inside's positive. So it looks like I'm on the positive x-axis. Here is 0. I do not want to include it. I need to also include this negative 2, right? Actually not. Right, so I want everything bigger than 0. So all this stuff is already out. Right, so I want all of this, do not include that, and then everything else. I want all the numbers between 0 and 2, along with all the numbers bigger than 2. That's the domain. Zero to 2, union 2 to infinity. Please.
How did you get that? 0, I mean, x is greater than 0. Where did you get that?
Oh, thank you. So I have the square root of x here, right? This is somewhere in the problem. I can't put in negative 4, right? Because so I only want to take square roots of things that are positive or 0. So I could have used 0, but I already knew that 0 doesn't count. That's why I left it out, right? So if I want to take the square root of anything, the thing needs to be positive. That's why I only pick stuff over here. The square root of only positive things. Right? Now my engineers will venture along in the future and you'll be using complex numbers all the time. Right? But in pre-calculus and in calculus, we're only dealing on the real line. Right? When we put something in, we want a real number to come out. If I were to put something negative in here, a real number would not come out. So I only want to take positive things. So once I saw this root here of just x, I knew that I would never take anything to the left of 0. Questions about this? Thank you. M of G and G of M. Okay, this is nice and delicate. This is good. All right, so then M of G, how good is this thing? Oh, it's that good. That's good. I'm going to take G, plug that into M, see where problems might come up. M of G of X. Putting G inside of M, 1 over the square root of X squared minus 4. So this is a topic we're going to talk about later, but I guess we're going to present it with it now, right? So now I need to make sure that this thing's okay. So I need to make sure that, so I need the domain of this. So we need x squared minus 4 greater than 0. I don't want it to be equal to 0 because that would make it the denominator 0. But we are going to set it equal to 0 because we need to solve this inequality. Right. So one of the things we're going to do is use some properties of parabolas and polynomials that we'll talk about more in depth later. Right. So we're going to use the trichotomy law. So the trichotomy law says that tri meaning 3, on the real line you can be only one of 3 things. You can either be positive, negative, or what's the other one? 0, right? So what you do is you set this thing equal to, so if you want to find the places where this is positive, then you need to find the places where it's 0, and everywhere else is either positive or negative, right? And so it's 0 at -2 and 2, and everywhere else it has to be positive or negative. Now you can also use some properties of the parabola, right? This is x squared minus 4. It's going to be 0 here and 0 here. What is it going to be over here, positive or negative? Bigger than 2. Positive. And less than -2? It's still going to be positive. That's right. So you can either graph it, you can do all sorts of things here, right? So I don't want these, right? But one of the ways that you can do this is you can test, right? You can pick a value here. So if you pick a value here, x equals 5. Pick a value here, x equals 0. And pick a value here, x equals 7. I'm sorry, -7. And you plug these values into this, then it'll tell you what the sign is going to be over there. So when x is 5, for instance, you get 5 squared minus 4. 25 minus 4 is 21. I don't really care what the number is. I just know that it's positive. When x is 0, 0 squared minus 4 is -4. It's negative here. And then when x is -7, -7 squared minus 4 is 49 minus 4, which is positive. So we're going to do a lot of this when we do polynomial inequalities. And we use this a lot in calc. But you can use the fact that this is a parabola, and then it rises to the left and it rises to the right. You can also reason that when x is bigger than 2, x squared is bigger than 4. When x is less than -2, x squared is still bigger than 4. There are all sorts of things you can do, right? The point is that the domain is all of these union with all of those. Anything between -2 and 2, when you square it, is going to be less than 4, makes this a negative. Questions about that? Set the denominator equal to 0, do a number line, pick values, and only take the positive stuff. That's what we're about. The Great Skeptic has come in. So the Great Skeptic is a character in mathematics that has progressed mathematics through some difficult times where mathematicians for some time have been doing hand waving. They'll come in and they'll say, oh, this looks right because of this and this and this, right? And the Great Skeptic says, well, wait, why, right? Why is it that I just get to pick one number here, and all of a sudden that number makes every number I pick a positive? Why is it that I can only pick -7, get a positive, and all of a sudden I convince you completely that no matter what number you pick over here, it's positive? Right? I need to demonstrate to you why that is. I just won't do that right now, right? But keep that in mind, that there are infinitely many numbers between -2 and 2. I picked one number, and now I'm claiming that they're all negative between -2 and 2, right? That's not something we should accept, just because I said so, right? So that's going to be because of the theorem that we demonstrate later. Okay, g of m of x. Going to take m, plug that into g. That's going to be m squared minus 4. Right? That's going to be 1 over the square root of x squared minus 4. And now we start to get a little funky. What is that? One over the square root of x squared, that's 1 over x minus 4. What's the domain? X has to be greater than 0? Is that right?
Can't it be less than 0?
Can it be less than 0?
Just can't equal 0.
Wait, so x not equal to 0?
Yeah.
What's the domain?
0.
So you're saying this?
Yeah.
Okay, this is good. This is being technical. Okay. So I'm going to have to do this on Friday. Be careful. Right, so the question is, what is this function? How did you get this function? How did we get this?
You just simplified it before.
I simplified
You simplified
that, right? Let's be clear, right? I took x, put it in the m, and then took that and put that in the g, right? What goes in the m? Remember m? M of x is equal to, is it not this? Is that okay? So I took an x, right? Put that in the m. Now the x I put in the m, is that this x? I asked a yes or no question. The x that I put into m is this x. Okay, good. I'm going to take x, I'm going to put it into m, I'm going to do something to it, and I'm going to put it into g, do something to that, and then I'm going to get something else. Is it the same x? Alright, so good. So if I put 4 into this, right? If I put 4 into m, is that going to be a 4? It's interesting. I guess you should try it. I guess you should try it, right? So if I put 4 into here, what do you get? 2, 1 over 2, and then 1 over 2 squared is 1 over 4. It is the same x, right? It's the same x. All right, now what are the x's I can put in the m? They have to be bigger than 0. I can't put any x's in the m that aren't bigger than 0. So the domain of m speaks the whole way, right? So it's like m is a door, and only the positive things can go through the door, right? And so when you arrive at the end, these things still have to be the same things that went in the m, right? So that's the subtle thing, right? And this is our fault as mathematicians, because we get super lazy. Because every time we want to write a function, we don't always write the domain and range, right? Right? So somehow we have to remember that the thing we get at the end speaks to the domain of m, not to anything else. Because when you look at this on its own, it looks like, oh, just make sure the denominator is not 0, right? But it came from something else. It came from some other process, right? I'm going to take any questions about the subtle difference here, right? So the story will go like this, right? The story will go on Friday. I'll say something about, I'll give you 2 functions like this, and I'll say, that you got this from the composition of 2 functions, right? And that the domain of m is a certain thing. What is the domain of this? Right? And you have to respect the domain of m.
So if, let's say for example, we get a g that has a similar case where the domain of g of x is completely different from g of m of x, we still consider the domains of g as well?
Well, I care about the range of g, not the domain. So yeah, so the mere fact that you're doing this, so when you go through this process, right, the domain of g is taken care of, right? Because you'll see how I wouldn't have put m in it to begin with, right?
So for these ones, it's always, we should take the domain of what?
It's about m. It's about the inside.
Yeah.
Yeah. Yeah, it's about m. Yeah. Floor is open for questions about this. Confusion about why the domain of this is x bigger than 0. It's because it's the domain of m. Okay. Good. All right, so word problem. The number of bacteria in a refrigerated food product is given by this ugly thing. T is between, N depends upon T. T is between 5 and 35, and T is the temperature of the food measured in something. When the food is removed from the refrigerator, the temperature is given by this function, where T is the time in hours. Plug one into the other. That just looks ugly. How good are they going to be here? Do we have to simplify?
Very gentle.
You don't. Okay, so great. So you will put 30. Great. So you will put 30. Let's see if it likes it. 30 parentheses 6t plus 1.5 squared minus 163 times that thing. May want to do some copying and pasting. Right? Plus 66. Oh, now they're being bad, right? Now you need to set this thing equal to this and solve.
So on the test, will we have to reduce?
No, it won't be this ridiculous.
Oh.
Yeah. So then, yeah, you would just see how long it takes to reach this. So here you might want to bring out some graphing calculators or something like this. Use the quadratic formula as a last resort. But yeah, I mean, yeah, I would probably use the graphing calculator just to set this thing equal to this and find out where they intersect. Questions on that? Say it again.
Oh, I thought you just solved it.
Yeah, no, yeah, you can go ahead and solve it. Yeah, but yeah, it's tedious. You don't need to do this by hand, right? You shouldn't do this by hand. That would just take forever. Yeah, so you can just plug this into Desmos and see where it crosses this, or plug this here, set it equal to this, bring everything to one side, see where it crosses the x-axis. Yeah, so I won't. If you skip this, that's okay. Composition. This is the composition of a couple of functions. They've given you one, so it's pretty much determined. The function h of x equals x plus 9 to the 8th can be expressed in the form f of g of x, where f of x is x to the 8th and g of x is defined by something, right? What is it saying mathematically? It's saying that here's h. H is the composition of two functions, and here's one. What's the other? H is x plus 9 to the 8th can be expressed in this form. This means that I could write h as doing two things to x. H does two things to x. H transforms x twice. Right. One transformation is raising something to the 8th power. What's the other thing that happens to x?
9 is added to it.
You add 9 to it. You add 9 to it. That's it. It's x plus 9. You add 9 and raise it to the 8th, right? So h takes x, adds 9 and raises it to the 8th. They represented f by raising it to the 8th. The first thing you need to do, right? The first thing you need to do is add 9 to it. G of x is x plus 9. Same thing, right? H takes x, adds 6, then flips it. Right, it's going to add 6 first, that's G, and then you're going to flip x. Flip x. So add 6, flips it. They've given you the first step, add 6, flip it, right? So in order to get the steps right, you go directly where x is, right? So you go to the innermost part of the function, and then you add 6. And then I think that's it. Oh, and there's a word problem, right? So here we are with units. This is kind of like the first problem we had on functions. The function d of p gives the number of items that will be demanded when the price is p. D depends upon P. The production cost, C of X, is the cost of producing X items. C is probably in dollars. X is in items. To determine the cost of production when the price is $5, arrows. Right? So 5 goes into D. And then that gives you, D gives you the number of items, and then C takes the number of items. 5 goes into D, and then that goes into C. That's right. So again, just arrows, right? 5 goes. So, and by the way, all the other ones simply don't make sense, right? Why doesn't the first one make sense? D is in what?
The number of items.
Items. 5 is in,
Price.
what are the units of 5 here?
Dollars.
Dollars. Right? So this is in items, that's in dollars. They would never be equal. Right? What's wrong with this? C takes what?
Cost of making X items.
C takes items. I wouldn't put dollars inside something that takes items. The cost might be $5. What's wrong with that? Well, that's the cost, and this was the price. They're just not the same thing. Okay. So the other ones just don't make sense in terms of the units. Okay. So this one here, right? All the units match up. That's in dollars for the price. D is taking the price, and then D returns items. C takes items. It's all perfect there, right? All right. Questions about this homework? This assignment 1.4. Please.
Question 9, the word problem one.
Yeah.
For the second part, to like, find the time needed, all it's doing is setting the, like what we got for the first part.
Equal to the, that's right, and using whatever technology or methods you would like to solve it. Yeah. Thank you for your question. All right, let's transform some graphs. We'll start with our favorite x squared. We'll do x squared, and oh, let's do this. It's f of x equals x squared, and now I want a new function, g of x. G of x is f of x, right? All right, so what I want to do is I want to change f by moving it up, adding some numbers to it, multiplying it by some numbers. We'll see what happens. So g is going to be f transformed. If I add a 5, what's going to happen?
You go 5.
Say it again?
You go 5 up.
5 up. Why is that? Because when I write y equals f of x, or when I draw the graph of f of x represents the y coordinate, right? So that if I take a new function, g, and say it's f of x plus 5, the street version is just saying, yo, take the old y coordinate, which is f, and add 5 to it. Add 5 to all the y coordinates. If you have all of these, all the red y coordinates, and add 5 to it, then it shifts the whole thing up 5 units. Adding 5 on the outside of the graph shifts everything up 5 units. I'll be talking a little bit about outside and inside, okay? And so when I say outside and inside, it's in reference to these set of parentheses here, right? The parentheses in which you plug something in the f. So g of x equals 5x. I'm sorry, g of x equals f of x plus 5. Of course, if I change this to a minus, then it would shift it 5 units down, right? And now, obviously, if I add an a, and then I slide a, then a, depending upon whether it's positive or negative, simply is a vertical shift. I'll take any questions about that. Of course, I could do a different type of shift. Right. There's F. I'll turn this one off for the moment. There's H. Right. I can look at some values here. Plus 1. 1 unit to the left. 1 unit to the left. Why is it not to the right? So at this is f of x. This is the original one, right? At 0, it's 0, right? I have f of x plus 1, right? 1 unit to the left. Why is that? Well, the question is, well, what would it take to get 0 again? Right? And I would need to plug in -1 to get 0. So when I have f of x plus 1, it's x plus 1 squared, right? So I've moved it. So I've moved all the x values 1 to the right. So to get back to the same place, I need to move to the left to counteract that. So if that's 0, -1 gives you the 0 that you had before, right? So if I change that to f of x minus 1, I moves it 1 unit to the right. So it's the opposite on the inside. It's the opposite on the inside. So things to take notice of, that when I was outside the parentheses, that was affecting the y coordinate. Stuff on the inside of the parentheses affects the x coordinate. Stuff on the outside of the parentheses is an up-down thing. Stuff on the inside of the parentheses is a left-right thing. Street version. This would be super useful when we start doing trig functions and transformations. Why are we doing this? We're doing this because, as again, pre-calculus is about functions, but functions aren't always going to be the way you want them to be, right? We aren't always going to be dealing with x squared. Sometimes we're going to be dealing with x minus 5 squared, right? Sometimes we're going to be dealing with 4 times x minus 3 squared plus 15, right? If we know the graph of x squared, hopefully we should know the graph of 4 times x minus 3 squared plus 15, right? Specifically, when you throw a ball in the air, right, it looks like a parabola, but it doesn't look like x squared. It looks like a transformation of x squared. I need to flip that thing. I need to move it to the right a few moments, and I'm looking at the top value. I want to know what that is, right? So we're going to be so the basic functions we have, we're going to need to think about, you know, when we look at something or when we want to model something, we want to transform it to something else, right? On the inside, it's the opposite. So if this is x plus b, right, I get the slide b, and that's the thing that's for sure moving left, right, opposite of what the intuition may tell us. When b is negative, it's on the right. When b is positive, that's on the left. So notice how they're on the opposite ends. That's on the right of 0, that's on the left. Please.
So if we write a quadratic equation, it's just ax squared plus bx plus c.
Yes?
What does b do necessarily?
That's a great question. So that b is not the way I ever think about it, right? So when we define quadratic functions, I define it differently. But you know what I'm going to say, given what I just said about how I think about it. When we define a quadratic function, I'm going to say it's like this. F of x is let me call it q. Q of x is equal to a times x minus h squared plus k. That's what I'm going to call it. So that if it is the case that x squared is the basic quadratic function, x squared is the parent of all other quadratic functions. And every other quadratic function is just a transformation of that one, right? So that the form that you gave me would be if you squared all this out. But then if you square all this out and get this funky b in front of x, that b is hard to figure out what that b represents. This is why I prefer to look at it like this. Because when you look at it like this, it'll be very clear what h and k and a do, right? Yeah. So it's better to have it unraveled than to factor it out. That's a good question. I'm going to take f and then I'm going to multiply it. Oh, let's do this. I'm going to take f and then I'm going to, let's call it p. P of x is going to be 2 times f of x. What happened there? This 2 is on the outside. F represented the y coordinate. I'm going to double all the y coordinates. What does this do? What's the word we use?
It's sort of like shrinking the rest.
Yeah, sure.
Shrinks it
Right back there.
Not vertically. Horizontally, yes. That's not the way we're going to think about it, right? Because if it's on the outside, then we want to talk about it in terms of being vertically, right? So it's a vertical, it's like you're steeping it, making it steeper by a factor of 2. So it's a vertical stretch by a factor of 2. Vertical stretch by a factor of 2. Now the great skeptic says, well, is it always going to be a stretch? If I have q of x is equal to 1/2 f of x, that's not a, you're not steepening it, you're widening it, right? Go ahead.
So when your coefficient is inside the parentheses, that's when you have to put it.
Say that again.
Like when you have a coefficient like inside the parentheses,
Yes.
that's when you have to put.
That you have to do the opposite thinking. Yeah, that's right. When it's on the inside, you do the opposite thinking. That's correct. Yeah. So here when I multiply by 1/2 on the outside, I'm now, f represents the y coordinate. I'm now cutting the y coordinate in half. All those y coordinates I cut in half. That means this needs to come down here. This needs to come down here. That's like widening it, right? On the outside, right? All right, now I'm going to do this same thing on the inside though. M of x equals f of 5x. F of 5x shrinks it horizontally. F of 5x shrinks it horizontally. Well, why is that? It's like when you put the 5 in there, right? So f originally will take x, for instance, f will take 1. F of x takes 1. 1 squared is 1, right? F of 5x is 5x squared. If you plug in 1/5 into that, you get 1, right? So at 1, you get 1, or for the second one, at 1/5, you get 1, right? By plugging in 5x, you get to numbers 5 times as fast, right? If you plug in 1/5 into m, you get 1, which is 5 times as fast as what it was before, right? So when you plug in the 5 on the inside, it makes things 5 times as fast to get to the same y coordinate, right? But the street version is that when you plug in 5, it cuts all the x values by 1/5, because stuff that happens on the inside affects the x values, and it does the opposite on the inside. It does the opposite on the inside. Okay. Plugging in a 5 there cuts all the x values by 5, the same x values that you need to get to the previous y values. Of course, you know that if I made z of x equal to f of 1/3 x, then it's going to take 3 times as long to get to the same y coordinate as before. That at 1, I get 1, but now f of 1/3 x, it takes 3 times as long to get to the same place. Let's just make that clear. There's y equals 1. That's right there. This is 1 for f. This is 3 for z. It takes 3 times as long to get to the same y coordinate. Because when you multiply the x by 1/3, it has the opposite effect. This stretches horizontally by a factor of 3. Stretches horizontally by a factor of 3. Classic test question on Friday is, here's f of x, and then I'm going to say, here's what g of x is. How does g relate to the graph of f, right? well, this is a typical question in the homework too. So we'll practice that in just a second. Questions there. On the inside is the opposite. We'll turn some of these off. Questions before I turn these off? Okay. All right. Running out of letters, but it's okay. T of x is equal to negative f of x. We know what that does. All those y coordinates that were positive all become negative. Reflection over the x-axis. Reflection over the x-axis. So we put, and this is not so shocking. F was the original y coordinate. I now put a minus sign in front of it. All of those y coordinates that were positive become negative and vice versa, right? I'll put it in a different function to do reflections on the inside, right? So if I do, we'll put in one of our favorites. So if I call r of x, I'll call that the cube root of x. That's this one. That was one of our favorite ones, right? And now I'm going to go up and I want to get rid of that. So now if I'm transforming that, if I do n of x is equal to r of negative x. Right? So now I put the negative on the inside. Then all the x's here, so very simply, 2 went to this. If I put a negative on it, and we want to keep the same y coordinate, right? Then it reflects it over the y-axis. So putting the minus sign on the inside reflects it over the x-axis. I'm sorry, putting the minus sign on the outside reflects it over the x-axis. Putting the minus sign on the inside reflects it over the y-axis. Okay. So you take the black graph and simply reflect it over the y-axis. I didn't want to do that with x squared simply because you wouldn't have seen the difference. X squared is already symmetric over the y-axis. Questions about that? That's all of them. We're just going to use them together, right? So then if I take, we'll turn this one off, right? So then if I take r of x plus 3 minus 6, it's not so shocking that it's that r of x plus 3 minus 6, the graph of r of x plus 3 minus 6 is the graph of r shifted 3 units left and 6 down. 3 units left and 6 down. What function would I have? I do d of x. All right. I'm going to flip r over the x-axis, move it 2 units up and 4 units to the left. Over the x-axis, 4 units up, 2 to the left. Over the x-axis, 4 up, 2 to the left. What's that?
That'd be negative r.
Negative r.
X plus 4.
4 up, 2 to the left. Questions? Yeah. Give you all sorts of nice pictures. Okay. Any questions about that summary of things? Okay. So, context from the college environment, again, that what just happened, of course, will happen to you, right? I'll come in, wave my hands the whole way, right? In the book, they have all these nice tables and stuff like this, right, that you can go and look up all this stuff, right? So, again, some of you may have seen this before. That's great, but just make sure that you're used to understanding that I'm not going to come here and give you a worksheet and say, here are all the things, right? So I'm here to give you the ideas. You can look at the book and get the tables and all of those summaries. Okay. Pre-calculus is a place where also, like, once you can sit here and absorb it and get it, right? And it stays with you if it's presented in a nice way. Hopefully it was just now, right? But again, we just need to be careful that the higher you go up, the more complicated it gets, and note-taking becomes very important. Let's try and hit the homework. It's 1.5. We're gonna burn through these. It looks like a lot, but yeah, it'll be pretty straightforward. The formula is f of x equals x cubed. This change by adding 7. What effect would the change have on the function's values? Shifts it 7 units. It would add 7 to all the y values. I think that's it, right? What effect would it have on the graph? It would shift all the points to the left. No effect. Shift all the points up 7. It's looking good, right? Yeah, I think we're gonna burn through these. Right. So yeah, this would be pretty straightforward because yeah, you're just gonna basically go through all the summary that we just went through, right? 5 to the left, right? X cubed is changed by adding 3 as shown in the red below. Which of the following best describes the resulting change for each of the functions? Right, so here x cubed plus 3. The plus 3 would directly affect the x value, so the graph would shift horizontally. Right, so that's A, right? Horizontally. Y value, so this one's vertically, right? Just summarizing, let's just go. Let's see how far we can get before something interesting arrives. Alright, so this is now, alright, so now let's see how to interact with this graphing utility. Move the slider K so that the graph of y equals x squared gets shifted up 3 units. Then type the new function f of x in the answer box. So here's where we just need to be careful on how to put this stuff in. That's x squared. What function will we like? Up 3 units. F of x equals x squared plus 3. Yes. And now we need to shift this thing, right?
Yes.
1, 2, 3. I think that's it. We don't need to press OK or anything, right?
What do those buttons on the bottom, right?
Say it again?
What do those buttons on the bottom, right?
Here?
Yeah.
I think this allows you, instead of using this, right? I think by default it's already up. But I think that you could have made it left instead and put it inside. Let's see if that would have worked. So then it does. No, that doesn't do that. Oh, that's it. I guess that's just the window. Yes, it just lets you look at the window.
And then it zooms in and out.
It looks like it is. Yeah. Is that okay? 2, 3. Questions about how to enter this. Well, let's see if that's right first. See if it likes it. Questions on how to enter that in. So we've interacted with a new graphing system. Okay. Two units to the right. 2 units to the right. So it already fills it in for you. 2 units to the right, and you would just put that right here. Two units up, 3 units to the right. Two units up. So the 2's on the outside. Let's make sure. 3 units to the right. X minus 3. That's not happy with this, right? I have to write f of x equals. It's okay. Both. And then let's see what h and k correspond to. H is the number inside, right? So 3 units to the right. The k is on the outside, so it fits the same notation that I was talking about. Let's see how bad these can get. We'll move on. Alright, there's g of x. Shifted 1 unit down and left 2 units. G of x is equal to... Wait, is that the third root or 3 times the square root of x? This should be. Okay, so that's 3 square root of 2 units to the left, x plus 2, 1 unit down, one unit down, 2 units to the left, 1 unit down. Let's see if it likes that. Okay, good. I asked you that. I'm going to leave that one to you. Let's see if there's anything that's going to be super crazy. You're just going to have to notice what G does to F. There's a table for F. Here's a new table for G. G has done something to F. And it's one of those. Right? So if you're doing something to the y coordinates, maybe. It looks like you've also done something to the x coordinates. Looks like you haven't done anything to the y coordinates, right? So that the second row is the same for both of them, but it looks like the x coordinates are different. Which one is it? There's G. So I'm going to take these out. It's not these, right? We didn't change the y coordinates at all. So that means that nothing on the outside should be happening to this, right? The question is this f of x plus 1? Or is this f of x minus 1? Which one is it?
X plus 1.
Which one?
X plus 1.
X plus 1 or x minus 1? I mean, you can check one, right? You take negative 3 and you plug it into this and plug it into this and see what you get, right? So when you plug in negative 3 into this, what do you get? Negative 3 plus 1 is negative 2. What's f of negative 2? Negative 2. It's this one. Okay. Street version, of course, is it looks like these are just this move to the left, right? And that's this. Right? So it's like you shifted all of these to the left by 1, but that means it's +1 because it's the opposite. So you just see what the transformation is and apply it. X +1, and then there's 1 for H. What did H do? Looks like the X coordinates are the same. The Y coordinates look like you moved them each down by 1, right? So H should be f of x minus 1, right? So just shifting 1 unit down. 10. Same exercise. 11. Up 54, 59 to the right. You can write that one. Which one is that? All right, so this one requires that you know what the absolute value looks like. We know what the absolute value looks like, right? It's just the V. Its vertex is at the origin. Absolute value of x, there it is, right? So we can cheat a little bit and say, well, I just really need to know where this point goes, right? And so we know that, right? Because then when we look at the absolute value of x plus 2 minus 3, right? It just moves there. And we're not so shocked by that, right? Because all you're doing is you're taking all the points and moving them the same way, right? So you can cheat by just saying, okay, I just need to know where this point goes, and then all points need to follow that one the same way, right? So obviously this goes 2 to the left and 3 down because I've added 2 on the inside and subtracted 3 on the outside, right? And so you simply need to do the same thing when you look at that graph and model the map, right? And just see how it's been transformed. And so this looks like it's been moved 4 units to the left, and that means it's got to be this one, right? Because the other ones have a minus. 4 units to the left and 3 units down is for sure that one. Same thing. So this one's pretty straightforward. Oh, what's that one? If things are nice, hopefully it's just a reflection and they haven't done anything else. It looks like it's just a reflection, right? There's the square root of x. It goes to the point 1, 1. Here's a transformation of that. It goes to the point 1, negative 1. Looks like it's just negative the square root of x. It can get funky if you start doing other things. Okay. We'll see that in a second, whether that happens. You might want to check one more. At 4, it's 2. At 4, it's negative 2. It looks like you just changed the sign. Right? Negative square root. Question? Wait a second. Oh, they're a bunch. All right, what's this one? All right, so it looks like it's been reflected over the y-axis instead, right? So hopefully that's it, right? And negative 4 is negative 2. It looks like it's the square root of negative x, right? Oh, that's it. That's it. Right. So that fully explains this whole reflection over the axes. Let's see how bad this gets. All right. We're going to talk about the exponential function. They tell you, we may not know all the properties of it, but what they do tell you is that the black one is the original one. I'm going to do something to it. Right? The green one looks like the black one reflected over the y-axis. The blue one looks like the black one reflected over the x-axis. And then the red one looks like the green one reflected over the x-axis. So we'll do this super carefully. Sweet. All right, so the original is one of my favorite functions. This might be my favorite function, period. 2 to the x. And so the green is reflected over the x-axis. I'm sorry, the y-axis, right? That means that the green needs to be put a minus sign on the inside of the function. A minus sign on the inside of the function reflects it over the y-axis, right? So that's a horizontal reflection. A horizontal reflection, a left-right reflection, means that you're changing the left-right variable, which is the x variable. The blue graph is a reflection vertically, which is a reflection over the x-axis. So that means that you're putting just a minus sign in front of the original function. Now, the red graph, I'm going to take any questions on these first two. Now, the red graph, I can get directly to the, I can go back to the black graph and do 2 things to the red graph, or just do 1 thing to the green graph, right? So I could, you're just doing both things to the black graph. So the red graph is just the black graph flipped over the y-axis and then flipped over the x-axis. So you just have both minus signs, right? And so that this is both. Right. All right. A few more minutes left. Let's see if there are any remaining issues in this homework. No, that's roughly the same. There's x squared. We're going to do a lot of this with when we get to quadratics. All right, but it's the same thing, assuming that they haven't done anything to the stuff on the outside. Let's see here. Here's f of x. F of x is x squared. So we know what x squared looks like. So we're going to do something very similar that we did to the absolute value, right? Turn these off. I could go back up there and rewrite. Oh. A of x equals x squared. All right, looks like I need to flip it. Negative a of x. Right. I can call that j of x. Right. It doesn't like j? Why doesn't it like j? Can I use L? Doesn't like L. I already used z. Is it telling me I'm at my limit of function use? Oh, I've defined a somewhere else. I thought I did. Right there. That's right. Let's just do this. Right, so then I could, let's just do this. Negative x squared. There it is, right? And so now it looks like I need to move this thing to the right or to the left. Right? So x minus 4, right? And it looks like I need to move it down some too. Minus 5. Right? That puts it right there, right? And this is how we're going to define a quadratic, right? We're going to define a quadratic as just a transformation of the original quadratic. Right? So I need to flip it, move it down, and so the question is, what is this point now? Now, it should not be so surprising what that point is. And then when we evaluate quadratics, that it's going to be this point that's probably super important. It's called the vertex. Right? And so you get the vertex simply by transforming this to this new point. What's the vertex for this one? 4 and negative 5. It's staring right at you, simply because of transformations. Right? So that when you've been given the definition of what a quadratic is, it's deeply intertwined with what makes sense. Right? The only hope is that there isn't a number out front that messes things up. Right? That is to say that if that is 2, negative 3, then it's just that, right? X minus 2 squared minus 3. Now, the question becomes, that is where it goes, but how do I know it's not that? Right? So that's why you probably need to check one more point to make sure it's right, right? So at 3, it says it should be negative 4. Well, 3 minus 2 squared is 1. 1 minus 3 is negative 2, right? But at 3, it's negative 4. At 3, it's negative 4. Is that okay? So this on its own, 2 to the left and 3 down, this on its own is not correct. Right? So you need something else. Right?
We should just put a negative on the outside.
That might do it, right? Here. Right? Because we need to flip it, right? So is that going to do it? 3 minus 2 is 1. Squared is 1. Negative 1 minus 3 is the negative 4 we need. So all right, we just left off the minus sign. So 3 points determine a quadratic. That should not be so surprising, as there are 3 terms in a quadratic function. So they're being super nice there. All right. Okay, excellent. What we'll do next time, we'll end there. What we'll do next time is that we're probably going to finish 1.5, and then we'll talk about inverses and finish the chapter finish chapter 1, and then we may move on to chapter 2 or review for chapter 1.
If we have the test and we cover some of chapter 2, will that content be on the test as well?
Everything we talk about on Thursday. When we talk on Thursday, I'll be very clear about the test.